So this video we will see Routh-Hurwitz principle for stability analysis of the system. So what is this Routh-Hurwitz? We will see one by one. Here the first one, we for a given system we need to formulate the characteristic equation 1 plus g of s h of s is equal to 0. So this is the characteristic equation of any system. For the given system, the first step is to formulate the system equation or characteristic equation. So this is a polynomial equation in terms of s. So here the Routh-Hurwitz says that necessary and sufficient condition. What is that is, for a given system, the characteristic equation, all the coefficient term must be a positive terms. Must be a positive sum. Here see positive, here positive. So if it is positive, then it can be a stable system. It can be a stable system. If one of the element or more than one of the element is a negative coefficient, that system definitely it is unstable. Definitely it is unstable. We can easily stay without doing any calculation. We can conclude. Again, the next condition is that the power S power term must be in descending order, that is a decreasing order. S power 5, S power 4, S power 3, S power 2, S power 1 and S power 0. So like this it is going. So all the power of S term must be present. So that time it may be a stable system, but we cannot conclude that it is a perfectly stable. These two conditions are called a necessary and a sufficient conditions of Routh-Hurwitz principle. Now again the condition for stable, once again first we will formulate the Routh array using a set of rules called the Routh array. So in that array, if the first suppose this is the formation of Routh array. Here we have S power 5, S power 4, S power 3, like this it is going. If the first column of Routh array, all the elements must be positive number, that is greater than 0, then we can say that the system is perfectly stable. If next and second condition, again in the Routh array, if one row all the elements are 0, that time we can say that it is a marginally stable system or conditionally stable system. That time the system is oscillate with respect to some frequency. That frequency can be calculated using the auxiliary equation. Based on that auxiliary equation, when we solve it, we have the oscillating frequency for that particular system. So this type of using these steps, we will see a number of problems in the coming videos. Thank you. Next problem. The feedback control system shown in figure is stable for what value? What is the value of k among the 4 choices? We have to select one. So first we form the characteristic equation 1 plus g of s h of s is equal to 0. So 1 plus, this is called these two blocks are in cascade, so combined together k into s minus 2 divided by s plus 2 whole square, and the h of s is s minus 2 is equal to 0. So when we simplify this by taking LCM and expand this equation, we have the characteristic equation like this. For this characteristic equation, you form the Routh array, that is s square coefficient is 1 plus k, and this is called s power 0 constant 4 plus 4k, and the s power coefficient is 4 into 1 minus k, 0. Cross multiplying, applying Routh array rule, and we have the result in the s power 0 term is 4 plus 4k. For stability condition, given that the system is stable, for stability condition, the first column of Routh array must be a positive value, that is greater than 0. So the first element is 1 plus k must be greater than 0. And the second element 4 into 1 minus k is also greater than 0. And the last one is 4 plus 4k, again it is also greater than 0. So for these three elements, we have written the terms. For this k is equal to, for this term k is equal to, you bring this k to the other side, or bring this minus 1 to other one, that is k is greater than minus 1. For this term is k is less than 1, and the last term for this k is greater than minus 1. So combining these three, we can write for suppose we take a k, for this term k is greater than minus 1. This also k is greater than minus 1. For this we have the term minus 1 less than k. Next one is k greater than 1. Sorry, k is less than 1. This is k is less than 1. K is less than 1. So combining these three, we have the result k is ranges from plus or minus 1. K is ranges from minus 1 to plus 1. Now we have to select the optimum one. Suppose we have the first case where k is greater than or equal to 0, but now this is not the case. We have to include minus 1 also, but here there is no minus 1. Right, k greater than 0, but this case is valid for all values of k greater than 0, even in infinity also it is valid. And similarly, only if k is greater than or equal to 0, there are two cases. Now here third one is only if k is ranges from 0 or less than 1. So 0, it can take the value 0 and 1. So when we see this, it is ranges from minus 1 to plus 1. 0 is also lies in between. So see the third case, it can take 0 value, okay. Also it can take less than 1. It can take less than 1, not equal to 1. It can take only less than 1. See the fourth case, it can take 0 value, okay, correct. The last one is k equal to 1. K equal to 1 also it is taking. But according to this one, k should be less than 1. So the correct answer is k lies from 0 to 1, less than 1. Among the four cases, we can select this is the answer. A plant transfer function is given as g of s is given like this. When the plant is operated at unity feedback configuration, the condition for the stability is what? So here given that this is called open loop function, and the unity feedback is unity. So from the knowledge of characteristic equation, 1 plus g of s h of s is equal to 0. So 1 plus g of s, this is g of s, feedback is unity. So again we combine, we take LCM. In this term we LCM, take LCM, and again this term also you take LCM, and finally combine all the terms. We have the result like this: s cube 2s square kps plus ki is equal to 0. So this is something like a PI controllers having proportional constant and the integral constant. Alright. So again applying to the Routh array, so s cube is 1, s power 1 is kp, then s square coefficient is 2, and ki. Simplifying, applying Routh array principle, and we formulated the array like this. Now for stability, the first column must be positive number, so ki must be greater than 0, and this 2 kp minus ki divided by 2 is also greater than 0. So simplifying this 2 goes off, you can become 0. This ki goes to that side, that becomes plus. So again kp is greater than ki divided by 2. Proportional constant is half of integral constant. So we check the values. So here kp value is half of integral constant. Again this value must be greater than 0. From the first condition we have ki is greater than 0, otherwise ki by 2 is also greater than 0. So the correct answer is, which will satisfy both the condition, both the cases, is this one, kp. The first case is the correct. Next problem. A open loop transfer function having a unity feedback is given like this. What is the range of k for which the system is stable? Very straightforward question. First formulate the characteristic equation. 1 plus g into h is equal to 0. So 1 plus this is g, h value is 1, h value is 1 is equal to 0. So formulated the characteristic equation, then form the Routh array s power 4, then s power 2, then s power 0. Then s power 3 term is 4, then s power 1 is 6. Just applying the Routh array principle and simplify the terms. We have the answer like this. Now for stable, the condition is the first column of Routh array must be a positive element. So therefore this 21 minus 4k over 7 by 2 must be greater than 0. That is 21 minus 4k greater than 0. This 4k was that side. So k value must be less than 21 by 4. K value must be less than 21 by 4. And also from this we can write k value is greater than 0. From this we can write k value is greater than 0. So combining these two we can write k takes the value between 0 to 21 by 4. So k takes the value between 0 to 21 by 4. This is the answer. Next question. The first two rows of a Routh table for the characteristic equation for a certain closed loop system is given us like this. First two rows. What is the range of k for which the system is stable? So very simple. We need to fill the remaining terms, that is s power 3, s power 2 is given. We need to fill this s power 1 and s power 0. So s power 1 is 2k into 2k plus 3 minus 1 into 4 divided by 2k. Again, so this term is s power 0 term is, so this entire term is multiplied by 4, and here we have 0. So 2k into 0 divided by this term, so that becomes 4. For stability, the condition is the first column of Routh array must be a positive element. So therefore this term should be greater than 0. 2k into 2k plus 3 must be greater than 0. So 2k, this 4 goes that side. We form a quadratic equation like this: 4k square, 6k again minus 4 greater than 0. When we solve this equation, we have two terms. K is greater than minus 2 and k greater than 0.5. So satisfying these two cases, we need to select the k. So k is somewhat here, that is greater than minus 2. K is greater than 0.5. So considering these two cases, we can select in the given choice, k value is greater than 0.5. That may be up to infinity. The k can take the value up to infinity. So this is the answer. Next question. The loop transfer function of a negative feedback system is given. What is the value of k for which the system is marginally stable? So marginally stable meaning that one row must be 0. So here we will formulate this characteristic equation. 1 plus g of s h of s equal to 0. So when we simplify, we have the characteristic equation like this. Using this equation, we formulate the Routh table. So s cube, s power 2, s power 1 and s power 0. For the system to be stable, let us consider the system to be stable, the first column must be a positive elements. So the first column for this element is positive. So when we simplify, we have, okay, so here we have 11. Here also we have 11. Here also we have 11. Minus 11k. minus 11k, so this term must be a positive, so this term must be a positive element, so this is also positive. When we this 10k minus 11k becomes 1k, k should be less than 60, k should be less than 60, 160, k should be less than 160. Now again using this term 11k is greater than 0, 11k greater than 0, again k value is greater than 0. So therefore k takes the value between 0 to 160. K value takes from 0 to 160. But here it is given as a marginally stable, that meaning that the maximum value of k. So here the maximum value of k is 160, beyond which the system becomes unstable. So this is called marginally stable. K takes the value of 160. 160 is the answer. The k value is 160.